Okay, here we go. We're recording. So I want to demonstrate some stuff with Mars, the MIPS assembly and runtime system, that we're going to go ahead and use for our first and probably second assignment. So Mars, this is a fantastic simulator that lets you simulate a 32-bit MIPS CPU and run assembly instructions, but you're doing it all in software. And so you can see over here, this registers tab is telling us all of the different registers we have available in MIPS, the 32 registers plus these special registers, and then the values that are in them. Some quick notes. Remember, K0, K1 are reserved for the operating system. AT is used by the assembler. PC is the program counter. It tells us what the next instruction to be executed is. And then 0 is read-only. You can't actually set the value of 0. And GP is a pointer to the global pointer's frame pointer. Doesn't always get used. Stack pointer points to the top of the stack, and so on. So the first thing we need to do is open up an assembly file. One slightly annoying thing, this menu is not very good. The first time you open something, you have to go back here to users and whatever else, and basically navigate and find wherever your code is. And I happen to have, here we go. I've got this test print function. I've got these two assembly files. So let's go ahead and open this. And so you can see when I opened it, it automatically went ahead and assembled it. And if I click this Edit tab, it'll show you the assembly code, and then this is the assembly code after the assembler is done with it and has kind of loaded it in to go ahead and be run. Now, some notes about the assembly code here. One, I've got this .text directive. So assembly code is very low level, but it turns out it's not as low level as it could be. We're able to put these directives in here. There's various other things we can do. .data directives. We can put comments in here. We can use pseudo instructions like li for load immediate. We actually can do some slightly higher level things that the assembler will take care of. And we can put labels in here that the assembler will take care of figuring out what the actual, hexadecimal memory location address is going to be. So we go ahead and put this code in here. What is this doing? Well, it's loading 5 into T0, 11 into A0. It's putting 1 into V0, adding these two things together, putting it back in A0, and doing a syscall. Now, what a syscall does, it actually tells MIPS that it would like to go ahead and run some code that's actually controlled by the operating system. The system call interface is going to be different for different CPUs, and there might be vendor-specific extensions and things like that. It's kind of a hack that tells you, I need to do some code that can't really be done in assembly, so I want to let the operating system run some code from someplace else. And so syscalls have a pretty solid semantics that's actually available with the MIPS documentation. Essentially, you stick some number in V0, and then you do a syscall. And based on what's in A0 and what number's in V0, the syscall will invoke different bits of operating system code. So 1 in V0, when a syscall happens, says, well, print whatever integer values in A0. What's in A0 is going to be 5 plus 11, so this should print out 16. That's the whole goal of this program. And then I don't have any return or exiting or anything, so at that point I should get that the program kind of like exited incorrectly or whatever. So this is the code here. This .text directive is telling me this is text of the program. It's not data, it's actual machine instructions, and so I'd like it to be put where all the other machine instructions are going, which tends to start at this particular address here in hexadecimal, 004, and then a bunch of zeros, which I can't really do that conversion in my head. Now, when the assembler gets a hold of this, you can click this button here to assemble it, and it'll go ahead and assemble. And so now we can sort of check out our columns here. Here's the addresses. Here's the code. This is actually the 32-bit machine instruction that this instruction gets turned into. And we're not listing out all 32 bits, obviously. We've got hexadecimal, which only requires 8 digits. Now, this is the code that we've written But remember, load immediate's a pseudo instruction, so this is what it's actually getting translated to, and you can see this constant value 5 has been turned into a full, 32-bit constant value, and so on. So you can see we've got this instruction, this instruction, this instruction to get things into T0, A0, and V0, loading those constant values in. We've got this add operation, and then we're doing our syscall. And you'll also notice that the register numbers, these are the sort of slightly higher level register names, T0 for temp 0, A0 for argument 0. These are getting just changed into the actual register numbers, $8 because T0 happens to be the 8th register, and $4 because A0 happens to be the 4th register, and so on, essentially converting it to the register numbers over here. And one other cool thing, you notice this is actually telling you the line number of the source code to go along with your assembly instructions, which might be pseudo instructions. And of course, you can always click this tab to sort of go back and look at the code. Let's go ahead and run this and see if it prints 16. Lo and behold, it did, and then we got the program is finished running, dropped off bottom. And that's just something that's been added in. Normally, you shouldn't do that, but Mars kind of understands that simple assembly programs, you've just got a few instructions, and then if you sort of reach here and there's no more instructions, that basically the program's over. Because there's not really an operating system to return back to. Mars is just a simulator. So you can see this run. Now, one other cool thing you can do, you can reassemble it to jump it back to the beginning. This button runs it. This button runs instruction by instruction. It's almost like a debugger. So we can run the first instruction and see, haha, look at that. 5 is now in register T0. Let's do another instruction. Haha, 11 is in register A0. Now, of course, we don't see this as 11. We see this as B, because what we're seeing, of course, is the hexadecimal value. But, of course, in hexadecimal, you've got the digits 0 through 9, A is 10, B is 11, so that totally makes sense. Run more instruction, we got something in V0, do another instruction, we just did an add. Now when we do the syscall, that's where we get the print, and then if we try to run one more instruction, the program's finished, we've dropped off the bottom. Cool thing about MIPS, you can actually sort of undo, right? You can sort of go back particular steps, because there's not really a lot of state from instruction to instruction, so it's actually really easy to go both forward and backwards in MIPS. It's actually much harder to go backwards in regular programming languages that aren't as simple, higher level languages like Java or C++ or Python or something like that. So this is kind of a simple assembly program showing us how to use syscalls to go ahead and print integers. And there's syscalls for a whole ton of different things you might want to do. And if you're not sure, you can always go find this. Where is it? Here we go. Under Mars, which is a project out of Missouri State, there's this whole entire specification of how the syscalls work. So like 1 prints the integer in A0. You can print floating point values, double precision floating point string. A0 will store the address of the null terminated string to print. This is where that .data directive, which we haven't really seen, but we will see, it's actually possible to kind of like specify what the string should be, and then the assembler will go ahead and convert that. We can read integers, we can read floats, we can read a whole bunch of things. There's actually stuff we can do to terminate execution so we don't sort of fall off the bottom of the file, read and write from files. You can actually generate MIDI sounds for different pitches. I mean, there's tons of crazy things you can do that's totally awesome. So if you're interested, once again, you just find the documentation for this and go check it out. So I wanted to show off one other very simple assembly program. Let me go ahead and open it. Where are you? Here we go, function1.s. Open that up. You can see there's a much bigger program, and it actually is making a function call. Pretty fantastic. So let me show you what's going on here. Here's our .text directive telling us, okay, here's a bunch of code. Fantastic. Here's main. Great. Love it. And here's this plus function that we're invoking. Now, more or less what this code is doing is actually pretty simple. We've got main. It's going to put 10 into S0, and then it's going to put 5 and 99 into A0 and A1. That's where the parameters go. Then it's going to invoke this plus function, so it's going to invoke this down here. Now, what the plus function does, actually pretty simple. All it does is add the values of the two parameters together and then return it. But it's doing it in a very particular way. I wanted to show off save registers. So let's kind of step through this and sort of see what's happening. So we're loading 10 into S0. Now we're putting 5 and 99 into A0 and A1. That's perfect because A0 and A1, those are the registers we use to pass the first two parameters to a function. JAL, that stands for jump and link. What that does is it jumps control flow to this label, so it's going to jump control flow down here, so we'll start going here. But the link part of it means it's going to take the address of the next instruction, which in this case is just a no-op, kind of here to not do anything and space out the code, and which has to do with branches taking an extra instruction. We're not going to worry about that till we learn about pipelining much later in the term. But you'll see this a lot, these no-ops, especially after branches and jumps. It's going to store the address of this instruction in the return address register so that when this function returns to the value in the return address register, it'll actually return to here, and that's where the code will continue running. We're moving the return value v0, so after we call this function, it returns its value by sticking it in register v0. We're putting that into A0. We're adding the return value of this function to S0. S0 we went ahead and put 10 in initially, and now we're putting 1 into V0 and doing a syscall, so essentially we want to print what's in A0, and then we want to put 10 into V0 and syscall. That actually ends the program, and it ends it without any error messages or anything like that. And if we look at this plus function, the first thing we're doing is we're going to allocate 8 bytes, so essentially 2 words on the stack. And we're going to subtract from the stack pointer. Remember, we always subtract from the stack pointer when we're putting things space onto the stack, because the stack grows from higher memory addresses towards the lower memory addresses, and that's just a standard convention in MIPS and many other assembly systems. Just a convention that's been built up over the years. Now we're storing the return address essentially 0 bytes off of the stack pointer, and we're storing the value in S0 4 bytes off the stack pointer. Now we don't actually have to store the return address here because we actually don't make any function calls. So since we don't make any function calls, none of the code in here between here and when we actually return this value in the register is going to change anything in the return address register. So we don't have to do this, but I'm just going to go ahead and do it anyway because you'll commonly see functions put the return address onto the stack. We're also going to store S0 on the stack, and the reason we're going to do that is there's some value in S0. S0 is a save register. That means my caller expects me, if I use S0, I have to put it back the way I found it. So the first thing I'm going to do is remember the value of S0 by sticking it on the stack. And then you can see I'm going to take these two parameters, A0 and A1, I'm going to add them together, put the result in S0. So I've clobbered whatever value was already there, but luckily I stored it in the stack. Now I'm going to copy that value from S0 into V0. Now I'm going to pull that return address off of the stack back into the return address register. That's actually unnecessary because I haven't actually changed the return address register, but I'm just going to do it anyway for symmetry purposes. Now I'm going to take that S0 value and put it back the way I found it by pulling it back out of the stack where it was. I'm going to decrement the stack pointer, so I still have some data sitting around in the stack, but I'm just going to put the stack pointer back the way I found it, jump back to the return address register, which remember, that's going to be where I did the function call, but the next instruction, so that's going to go back to here. And then I've got this no-op here. We'll learn why a lot of times these get put here later. This would work just fine if I took these no-ops out. If you don't really like these no-ops, you don't actually need to have them there because they don't actually do anything in this particular simulation. So we're showing off a couple of cool things. We're putting something in S0. We're calling a function that uses S0, right? This function's putting something into S0, but it's also storing it on the stack and restoring it from the stack. sort of showing off how this called function uses S0 but puts S0 back the way that it found it, and then we're jumping back to the return address. So let's go ahead and reassemble this and run it and see if it does something reasonable. So it printed out 114 and then finished running normally. That's great. That's exactly what we'd expect. We'd expect to get 99 plus 5, 104, plus 10, 114, right? The 99 plus 5, that's what this plus function does. It adds its two arguments together and returns it by putting the result of that addition into register V0. And then when we get back here to main, well, main's going to take the return value, which should be 104, put that in A0, and then add S0, which should still have 10 in it, and it does, together, so that should be 114. Then we're going to go ahead and print whatever's in A0, which is 114, and then we're going to put 10 into V0 and do a syscall. That's what causes the program to exit normally. So it's a very, very simple assembly program, but we're making a function call, we're storing and restoring the return address register, we're storing and restoring one of the save registers, and we're doing all that on the stack. And we're also making a couple of syscalls here back in main, and we're jumping back to return address register. We're doing a lot of the really important things that we need to be able to do in assembly code. One other note about Mars, we have this option here, initialize program counter to global main if defined. So you'll notice I put main first, not plus. Theoretically, I should be able to put plus first, then main. And if I have this option checked, the initial program counter, when I reassemble the program, should actually, point to wherever main is. But I can't seem to get that to work. So to make things easy, just put main first, and then you don't have to worry about it. So that's one note. Another note, I right now have assemble all files in directory turned off. Otherwise, as soon as you open an assembly file, it's going to try to assemble all of the .s files in that directory, which will have some weird effects. Watch this. If I say assemble all files in directory, and then I go back here to test print, and I tell it to assemble, look at this. I've got test print, but then I've also got, like, sitting after it, a bunch of the code from the other assembly file. So we just have sort of a lot of stuff going on here. So I might want this for some projects where I need all the assembly files in the directory, but in this case I don't. And so now if I sort of go back here and reassemble this, now I've just got the code that I wanted, which is nice and clean and simple. Okay, that's all for now. Thanks for watching.